Hi everyone, this is Rajesh Minawali from PayPal. Today I will be presenting my work on deep reinforcement learning for goal-oriented dialogue systems. So first I'll go with the introduction to the dialogue systems. Then we'll see why we need RL, current system and limitations, vision, and some use cases. Also, we'll see adoption of RL for dialogue management, RL architecture and components, and few experiments and results, and ongoing and research and next steps. So here's an overview of like what we have at the PayPal. So we have Chatbot for customer service, where the goal is to resolve the customer issues very quickly and cheaply. So we have about 40 most frequented contacted reasons and been expanding to 200 intents. We resolve 50% of the cases without human intervention in these cases. The remaining 50 do get routed to the human agents. Um, for the chatbot solutions, we have two, actually three right now. One is the IBM Watson. There's also an in-house model which we built on the transformer architecture. And more recently, we started leveraging Google conversational AI agent. All these three have few issues which I'll be going over in the next slide. But the in case of the channels, we have text-based channel. Also, we have the IVR, which we are slowly increasing the coverage from 40 to 200. And also, we have several locales and regions. Although we started out with English and primarily US centric, we have been include. So you have these NLU, which identifies the intent and extracts any entities which are needed for the dialogue. So there's a state tracker which keeps track of like where in the dialogue you are in. And that also does there's also a rule engine and a dialogue flow. So you can think of dialogue flow as a decision tree where once you enter a particular intent tree, the flow will guide you through the remaining part of the conversation until you either resolve it or move on to a human agent if you cannot solve it. And there's also a optional natural language generation, or you could go with a template-based text generation as a response. In the backend, you do need to store all the chat logs. You have a knowledge base or a backend system where backend system serves the account related, like what is the account number, the transactions which have happened in the past, and so on. So now the question is, uh, we have this system, so why do we even need a RL chatbot? So when we look at the overall system which is needed to run this entire system, there are four main components, as you saw. There's the intent, entities, then there's a dialogue tree, and the rule engine, right? So the SMEs spend quite a bit of time in defining these. And more often than not, like even though you have a dialogue tree which you have built in the beginning, if the rules change or the business priorities change, you need to modify that dialogue tree. So if you think of 200 intents, imagine changing 200 decision trees, and each tree has like maybe like 10, 15 depth, and you are looking at a gigantic system which is unmanageable. And also the time to market is quite high. As I said, like if there's a failure in resolving a customer request, the SMEs have to go through a lot of chat logs and see where the bottleneck is it in identifying the intent, or in extracting entity, or maybe the flow itself is quite wrong, that you might have to change it. So going back to these, just breaking down like the different building blocks. So there could be like intents which are 100 to 1,000 entities, again in the same region, same ballpark. There are also different channels, as I said, chatbot, text-based. There's also a language and locale, as I said, and dialog flow by nature has a lot of limitations. And as I said, like there is a need for continuous fine tuning for products and language and user preferences, which do keep change. Um, so here is just a quick overview of like how the design dialog flow design looks like. As you see, there's a welcome, which is the root node, and you continue through the tree. And if you just zoom into one of the nodes in the tree, you see that, for example, this is for some order, management. There are quite a few fields you need to look into, like the order needs the device, brand, price, and so on, and you need a confirmation. So if you want to change any of these, you would have to go through. Let's go to the next one, where you can think of like at each node you have a condition and then a response, and for each response you have for each node you have a child node, and so on. So any issue you have at the root node, it will circle back to the root node and try to identify a node which matches that. So the RL solution will be a guided flow with optimal response um, at every step, and constantly exploring, and it can adapt to the environment. And not only that, as I said, you don't have to have a human to identify each of those nodes. So the grand architecture for a RL based agent would be something like this, where instead of those four components where intents, entities, and dialog flows and rules are now replaced by what we call as a policy, reward, and penalty. So I'll be going over what each of these mean. Uh, the the goal here is basically the bot continuously learns whether an issue is resolved or not. So if the issue is resolved, it's well and good. You store it in the chat history as a successful dialogue or conversation. If it does fail, like if it cannot solve a customer request, it will be routed back to a human agent who will then go ahead and solve, and that will also be noted in the chat history. So over time, like as in the beginning, if there is a new flow, for example, recent COVID issue, we started seeing requests which were not seen before. So those will obviously be routed to humans in the beginning, as the RL agent would not have learned anything from the past. And but once those requests are resolved by a human, now chatbot knows what those successful conversations look like, and you will see a gradual improvement in the customer satisfaction. So what is an RL? How is it different from a traditional supervised algorithm? So in a traditional supervised algorithm, you are only looking at the current state and just making a decision. You have no idea of like what the future states would look like, or what path to take to optimize your overall satisfaction or success of a conversation. So here is just a example. Like for example, uh, customer 2 and 3 might end up on the same node, but they might have a different intermediate stage and also the final decision stage, right? So some might need a partial refund, for example. This is a refund request example, and some might have a decline. So based on that, you might have a different intermediate stage. In a traditional supervised algorithm, you would make a decision. You have to either pick this or this node, right? Whereas in RL, knowing the current state, it might route you to a different intermediate stage. And also, it might, for example, like even though you might end up here on a different node, you might actually just bypass and say, okay, I'm going to decline your transaction, right? Or a refund. So basically, the differentiation is it's a sequential decision making system, as opposed to just single decision which happens in a supervised algorithms. So there are here are a few examples in the industry where the chatbot has been utilized. I won't go over into the examples. You can take a look at these, and there are most of these happen to be more of a very small talk or a chit chat, as you can call. But these are very limited in nature, and there's still a lot of research going on in how to make this the mainstream way of interacting with the customers. There are also a few challenges. You might have heard reinforcement learning in different contexts, especially in games like Atari games, the famous uh, uh, algorithm showcased by Google. Also, you see these applied in the robotics. But unlike these games or in robotics, the breadth is quite large in a dialogue system. So there are a number of ways people might express the same message. And also, unlike in games where the episodes are quite large, like if you take an example of chess, it might have like 150 turns, whereas in a chat, at least in PayPal, what we see is most of the customer interactions happen only like 10 to 15 turns. And also in a game, even if you make a small change, you may not it may not be a blunder. You could still win the game. Whereas in a chat, if you make the wrong turn or ask the wrong question, because the number of steps or turns are limited to like 10 to 15, the impact is quite large. So you need to be really sure like what path to take in order to resolve the query. And also in games and robotics, there's a precise dynamics. There's like a predefined rules of like how a chess needs to be played, whereas in dialogue there is no it's pretty much driven by a customer, and each customer is unique. And the one good thing though here is, unlike in games where user and agent might be competing each other, here actually they are trying to achieve the same goal, which is basically answer the customer query. Um, and all these, like when we say a sequential decisioning, we are making what we call as a Markov decision process, right? Uh, where you assume there is a strict one state to another, where there's a turn by turn. Whereas in reality, what happens is customers actually might uh, converse in multiple turns. So they might type something and then hit enter, and then you go on to a next stage, and it may not be the appropriate way to respond. So you might want like whereas a human agent might wait for the completion of the message from the customer before responding. Whereas in the way you would design is like every enter from the customer is treated as a request, and you need to respond with some answer. So and also like the request from the text from the customer may not be relevant to your immediate utterance. So you might have to go back, like say 2 3 turns before you go in you actually respond. So you cannot assume that every request is a valid request. And also the way we set up the MDP, the Markov decision processing, is we assume that the user is initiating. In some cases, what happens is the user might have already contacted in a different channel, or maybe a day before, and is just trying to recontact. So in many cases, we want to set up what we call as an omni-channel platform, OCP, where we have a prior context, like why the user is here, because he has already contacted the day before or 2 day before. And we could pose a question saying, are you contacting about XYZ, right? So there is a conversation which is initiated from our like from the PayPal side instead of the customer side. So these are a few of the assumptions. Again, like we could make changes to the system, but what I did was I assumed that the initial context is always by the user. So here is the RL dialog management architecture. So how we design. So because we are focusing on a dialog tree where you need to clearly define a node, so this is where we leverage. The first step is basically to map these text into a embedding vector. You could use BERT, or you could use a deep averaging network where basically you're using the embedding vector for each word into translated into like for the entire sentence or the utterance. And once we have the embedding vector, now we need to specifically map it to a particular node in a dialog tree. And uh, this is achieved by clustering our utterances. So here, what I did was I combined I split the customer utterance and agent response into two different clustering algorithms. Clustering experiments, so that the rationale behind here is customers actually uh, express the same message in quite a different way, whereas the agents are usually typically trained in the same manner and have a very unique or very monotonous response. So uh, even though user utterance might have a variety, the response from agent might still be the same. So you want to separate that out. But the goal here is basically like from the raw text, you have an embedding vector. From the embedding vector, you now have a very discrete space instead of a continuous space, which happens to be in a dialogue. And that can pass through a error model controller. So here basically the idea is there are upstream uh, errors which could happen. So imagine a phone call, right? So there is a speech to text conversion, and there are errors which are introduced in the speech to text conversion, and you want to account for those such errors. So because of the text error, speech to text error, the embedding might be quite different. And from because the embedding is different, the cluster which is representative of that embedding vector might be different as well. So here what we do is we randomly introduce some Gaussian error to these representations, and then we feed it to the dialog state tracker. And the goal of the dialog state tracker is basically to construct the state representation, so that you have a entire history of what has happened. So in my case, the state is basically a concatenation of the current utterance, but also the previous utterances, or the cluster IDs of the previous utterances, and also the previous agent responses which has happened. Plus I also have a representation of what state you are in. So as I mentioned, like typically the dialogues happen like 10 to 15 turns, and we want to limit that, instead of like the dialogue carrying on forever like in an infinite loop. We want to make sure there is a definite end to this dialogue. So we limit the turns to be 20. So if it runs more than 20, we want to cut it off and saying, okay, let's transfer it to a human agent to resolve this, as it's not being resolved in even in 20 turns. So the dialog state tracker, what it does is it adds the how far are you along. So you might be like 5 of 20 turns. So it indicates to the DQN agent, which is the learning algorithm, saying, okay, you are nearing your end of the approved limits, which is 20 here, and you want to make sure you complete before that, or at least suggest to be transferred to a human agent. And the DQN agent here is basically takes the state and spits out one of the actions. So again, here the action is basically one of the cluster responses, right? So here, if you remember, as I said, like I am splitting the clustering into two different parts. So the agent part is also clustered, and the action selected is one of the responses, or which is going to be a pre-canned response. Of course, you can always replace this with a natural language generation so that it's a customized response. But for now, we are going with a uh, uh, placeholder method to send the response back. So there are different ways you can set the state and action. I will focus more on the reward function. How do we provide a reward, which is this is how the algorithm would learn, right? So what is a successful conversation? How do we measure, like, and also how do we measure the human likeness, or how do you optimize for short and long conversations? So there will be some conversations which happen only like maybe 2 turns, and the customer is happy, and there are some where it's quite complicated uh, request, and you need to go through multiple turns in order to resolve. And also, like, how do we handle conversation stuck in an infinite loop? I think this is kind of addressed by those that final uh, concatenation of the feature vector, where I mentioned, like, how far are you along those approved 20 turns, right? For a successful conversation, I just chose few positive sentiments, like saying thank you, or negative conversations, like where they say, "Can I speak to a human?" Um or if they say, like, "This is not what I meant," and so on. So there are limited ways people express either satisfaction or dissatisfaction. So I take that as a reward or a penalty, right? Going to the I think the clustering, I think is a standard deep averaging network. So I'll just skip over this. In its You can refer to Google's paper on this, how they combine, how they encode a sentence into a fixed vector. Okay. uh, so there are also different ways of clustering. I just mentioned I cluster. So in the initial experiment, I went with the usual k-means clustering, but there are other ways to do that. So this is one of the deep clustering where you have some labeled data with you for some of the intents, and you want to cluster them. Have that knowledge of the labeled data in your clustering algorithm. So there is a deep clustering algorithm. Maybe it's this for another talk, where I can go deeper into how you can leverage the label data in a unsupervised clustering algorithm. Okay. Uh, there are several blocks which you need to focus on. So one of them is the user simulation. Like, unlike in a supervised approach where you have a input and a output, which is the output label, here you need to go through the dialogue, right? So there is a structure to how you train your model, because it's not a one state model. There is a sequential decisioning which needs to happen. So the user simulator basically simulates that dialogue from your historic chat logs. Uh, the other the other method is basically you learn your dialogue conversations with through historic chat logs, but you could apply that a live interaction where a human might involve in fine tuning the final model. So you learn, like, say 90% of 95% of your training happens in using a user simulator, but the final mile can be achieved from SMEs, where they can dig through only those conversations or dialogues where the model was not able to learn efficiently. They can go and fine tune those final stretch. So error model, I think there are different ways of introducing the error. Here I just did a cluster ID, adding a cluster ID error. But instead of randomly assigning a cluster, what I did was I computed the distances from the cluster to the nearest clusters, and as a proportionally assign those nearest clusters, which is representative of these speech to text errors or maybe errors in how you embed your sentences. Okay, this is just a typical DQN agent. You could read up on this in any of those the articles on DQN. So this is a training example. We had about 1 million utterances and 50,000 unique sessions, and the conversations were selected where we only selected where the turns were less than 20, and also we skipped any turns where the first customer utterance is that of the agent initiated, and we only focused on user initiated conversations. And we went with the typical k-means clustering, where for the intents, which is the user utterance, were about 360, and the agent actions were about 478. And this is the distributions of the number of utterances per conversation, just to give you an idea. And as you see, like most of them tend to be less than 20. And here are the few experimental results. And here we got an average reward per episode to be about 23, although the max is 40. So for a success, this is how we define the reward function. So if it's a successful conversation, we gave a 40. If it failed, then we gave minus 20. For any successful turn within a conversation, we did not assign any rewards. But if the user had to repeat the conversation, then we gave a minus 2. And again, these are something you could experiment with different reward function, but this is what I came up with. So assuming the max of 40, we are achieving about like 23. Again, there's lot more you can do with in terms of the how you cluster and what kind of granularity you want those clusters to be represented. Uh, Again, we penalized both short and long episodes the same way, but this could be another experiment you could try. Can we do better? Like I use DQN, but there are other methods like policy gradients uh, and actor critic methods where you could apply different algorithms to fine tune it. And rather than restricting it to clustering, you could go with a more continuous space state and action representation. So the primary use case for us was mainly building this dialog flow builder. Basically, if you throw in a chat history, how do I come up with this dialog flow? So this is more of an intermediate step where I use the RL agent to come up with the dialog flow and use that in one of our solutions, either through Google's AI or the IBM Watson, where we are manually building this dialog flow. And so these are some limitations. As I said, like this all boils down to the granularity of our dialog flow because the clustering happens at a much higher level than the fine tuning. So here you can see that the actual conversation actually was quite different, but because of the way we are clustering, the dialog flow assumes you're asking the same question because they all map to the same cluster. But again, these are the limitations, but you can always fine tune with your clustering algorithms. Okay. So this is my final slide, and I'm going to showcase like what are the ongoing research and also the next steps. So as I glossed over, like some of the finer details where how you define a state and action, the reward generation or the user simulation. There's a lot more academic research which is going on, and each one is an area by itself. Um, and I would suggest the listeners to dig deeper into each of these areas to get fine tune your models. And also, the NLG is another area where we can customize the agent responses, and also exploring other algorithms. As I said, like here I am assuming a discrete space For that, I applied clustering algorithms. But you could think of you can think of other algorithms where you don't have to rely on the discrete space, but instead apply some of these methods and use natural language generation to customize your agent response. There's a whole area of adversarial inverse reinforcement learning where yeah, the goal is to just shadow the expert agents and learn a dialogue policy, which is rather than you coming up with a reward, what you can learn, what you can do is not only learn the policy, like optimize your policy, but also do a reward estimation. So you can do a joint reward estimation and policy instead of just doing the policy. There's also the final, or not the least in any sense, but this is the imitation learning, where you're basically mimicking a human agent and applying the reinforcement learning on top of that to come up with a agent which almost mimics your human agent or expert human agent. Okay, that's the end of my talk, and I would be happy to take any questions. Thank you.